Now we're going to move forward with a key application of probability, which is expected value. We begin with our friend, the four-sided die. So as a reminder, this is a die that the top indicates the result when you roll it. Only 4 options. If it comes up a 4, I give you $20. But if it comes up a 1, a 2, or a 3, I give you nothing. Now, what can you expect to get on average from that game? How much money can you expect to win? Well, it's tricky, because for any one roll, you have a pretty high chance of getting nothing. 3 out of 4 times you'll get nothing. But 1 out of 4 times you'll get a lot. So how much can you expect to win? Well, again, it's tricky, but what we could do, we could imagine 100 games. If there were 100 games, how many ones would you expect to have on average? That's right, 25. How many twos? Also 25, right? 1 out of 4 chance of getting any one of these, 25. So we would expect to get 25 ones, 25 twos, 25 threes, 25 fours on average. Right? That's what we would expect. That means you would get 1 25 times and get 0, 2 25 times and get 0, 3 25 times and get 0, and 4 25 times and get 20. How much money would you expect to win overall? Well, that's 0 times 25, plus 0 times 25, plus 0 times 25, plus 20 times 25, which is, of course, 500. In other words, you play this game 100 times, you would expect $500 total at the end, on average. You recognize, of course, that the roll of a die is independent. Maybe you hit 4 an unusual amount of times, maybe you don't hit 4 an unusual amount of times, but you would expect $500. Well, if you expect $500 to do it 100 times, then you know the average. For any one roll, it would be $5 on average. This is the expected value of this game. $5 is the expected value. The expected value is the average. Now, doing all this is kind of an annoying thing to do. It would be nice if we had an easier way to get to $5. And indeed we do. Rather than imagining 1,000 games or 100 games, let's just take the probability and multiply it by the outcome. And do that for every single thing that can happen. So the chance that something will happen times the payoff or the value if it does happen. It's important when you do this that you consider all possible outcomes. In this, that's very simple. There's only 4 possible outcomes. But it's something you always want to keep in mind. And then you are going to think about the payoff for every single one of these options, the expected payoff. And then say you can make money this way, or this way, or this way, or this way. In other words, you add them all up. So 0.25 times 0 is, of course, 0, and 0.25 times 20, add them all up. It's the same story. It's exactly the same story. And mathematically, you're seeing I'm doing exactly the same thing. Just multiply the numerator and the denominator by 100. But it's exactly the same thing. This is expected value. Expected value is essentially the average result of any probabilistic outcome, the average expected value. It is the probability that the ith thing will happen, the ith, the first, the second, the third, the fourth potential outcome, times the payoff if that ith thing happens, if that first or second or third or fourth things happen. And then you take all of those products, all of those different scenarios, all those different possibilities, all those different amounts, and then you add them all up. And then you divide by the sum of the probability. You'll note that this is exactly the same as weighted average. This math is exactly the same as weighted average, except I say P instead of W. And the reason why is because P is the W, P is the weight. There is a 75% chance I'll get nothing. So I'm going to put greater weight on the nothing. There is a 25% chance I'll get 20. So I'm going to put less weight on that $20 outcome. It's exactly the same idea. In fact, so much so that because I told you, remember, I said you have to consider all the possibilities. Well, the sum of all the probabilities is going to be 1, right? Assuming you know them all, which you should. Otherwise, you can't really tell the payoff. Because the whole idea is one of those things could happen. This simplifies to 1. You get that. Don't do the things that people love to do. Well, they will calculate the, each component of this, and then they will add them all up, and then they start dividing by like all the different possibilities. You've already done that. You did that when you did this P part, the weight part. So if you know how to do a weighted average, you know how to do an expected value. The math is identical. Let's turn to another another idea. This is the outcomes we had for our construction example. Here, just as a reminder what this looked like. Now, here's our different possibilities, here are our different avenues, and then we put them in order so that we can figure out all the different ways to get to 12 months of construction, 13 months of construction, and so forth. So there is a 0.8% chance it'll take 11 months, a 7.6% chance it'll take 12, and so on and so forth. Well, what would be the average amount of time? Like, let's imagine we had a lot of different jobs that were just like this. What is the average amount? What can we expect the job to take doing the weighted average? Well, you don't want to take 11 plus 12 plus 13 plus 14 plus 15 and then divide by 5. You don't want to take a stupid average. You don't want to take a straightforward average. Oops. And then you walk away and like, obviously it's 13, right? Of course it's 13 because it's halfway here. Because these are much more likely than these. Right? 13, 14, and 15 are much more likely than 11 or 12. So you want to do a weighted average. You want to do an expected value. The probability of something times the result of that something. The value you care about. Double click, and then of course we sum up. We get 13.8 months. Of course, you can also do the same thing too with the sum product option. Highlight that one, highlight that one, same thing. And just in case you were curious, yes, we have considered all the options, all the possibilities. So note this is 13.8. It's a little closer to this, much closer to the 14 than it's 12, even though the straightforward average is 13. Of course, because 14 and 15 are much more likely to occur than 11 or 12. The expected value is closer to 14, much closer to 14. Let's go back to our die example. So we determined that the expected value of rolling the die is $5. How much would you be willing to play this game? For me to roll a die, and then if it's a 4, you get 20, and if it's 1, 2, or 3, you get nothing. How much would you be willing to pay me to play that game? Now, of course, there are no right or wrong answers here. It's up to you. It depends on how you feel about it. Some of you might say 5. Some of you might say only 4 or 3 or 2. Some people might say 6. or 7. These different results reflect different attitudes towards risk. Rather than saying how much we were willing to pay, let's make it even more explicit about the choices. What would you rather have? So I have 2 choices. You can play the game, or you can just collect $5. You can't get 20, but you also can't get 0. So would you rather have the explicit payoff or the uncertain payoff? Again, there's no right or wrong answer here. It's effectively the same thing as saying, what would you rather pay, right? How much would you be willing to pay? If you're willing to pay only $3, then you would obviously rather go with that 5. If you're willing to pay 6 or 7, well, when you choose this, you are giving up on 5. If you choose this, you are giving up on $5. So it's the same idea. Which one of these you prefer determines your attitude toward risk. Consider this is A, the certain payoff. And this is EX, the expected payoff. Here are the 3 basic attitudes towards risk. There's only 3 options. You can either prefer A, you can prefer EX, or you can be indifferent. You can prefer to go for the certain payoff, prefer to go for the uncertain payoff, or just not really care which one. And we have specific names for each of these 3 kinds of choices, 3 kinds of preferences. You can be risk averse. You want to avoid risk. You will happily go for the certain payoff than the uncertain one. You are risk loving if you go for the uncertain payoff. So let's roll the die. I love risk. I love the thrill. Okay. Or you just don't care. You're like, it's the same thing. If you were to pay, a risk averse person might only be willing to pay $3 or $4 or maybe even $2. Depends on how risk averse they are. A risk loving person will gladly pay 6 or 7 or 8. Depends on how risk loving they are. A risk neutral person will always only pay 5. Right? Or they might be indifferent, essentially, between 5 and playing the game. Now, it's inaccurate to think that some people are risk averse and some people are risk loving. Your attitude toward risk typically changes based on circumstances, based on the kinds of how likely is it to win, how big of a payoff it is. So there's a lot of research into that area. We're not going to get into that. That's a whole psychology, economics area. It's a really cool area, but we don't really have time for it. But what we can do is we can identify how certain industries change and how certain industries are built around people generally having different kinds of risk preferences in different scenarios. The simplest one is gambling. So a roulette wheel has 38 spaces on it. An American roulette wheel has 38 spaces on it. Now, there are red spaces, there are black spaces, there's a couple of green spaces, but let's focus on the coolest payoff of all, right? There's payoffs for if you land on one versus the other, but the biggest payoff is if you choose one particular wedge of this wheel, one particular space, and it lands on that space. The payoff for if it lands on that space is 35. If you put $1 down and it doesn't land on the space, you lose $1. If it lands on that space that you chose, you get that $1 back, plus they give you 35. In other words, the payoff is a multiple of 35. So to show you an extreme version of this, if you put $1 down on everything, on all 38 spaces, well, you're guaranteed to win, but you will not make money because you will win 35 on the space that actually turns up, but then you will lose on all 37 other spaces. So you will lose $2. Win 35 from the casino, but then lose on 37 other spaces. So it's a guaranteed loss. So don't do that. We can figure out what the expected value of playing this game is. The probability of winning, 1 out of 35, 1 out of 38, times the payoff if you win. So if you put $1 down, you will then win 35 if you want. We'll just assume it in $1 to make things simple. That comes out to 92 cents, roughly. However, that's not the only thing that can happen. We can also lose our money. That will happen 37 out of 38 times. Payoffs can be negative, right? If it's a loss, it's negative, of course. In that case, it's about negative 97. Negative 97 cents. So playing roulette, whenever you put $1 down, you could win 92 cents, and you could also lose, on average, 97 cents, which means, on average, you lose a nickel. If you play this game 1,000 times, on average, you will lose a nickel every time you play the game. On average, you will lose 1,000 times, what is that, 50 bucks? Play the game 1,000 times, lose 50 bucks. Right? Yeah, it's possible that you'll make more. It's possible also you'll lose less. It's possible you lose more. It's possible you lose less. On average, you're going to lose money. So if you put $1 in all 38 spaces, then you are going to you're going to lose $2 at that result. Now, 2 isn't negative 5 cents, but if you lose 5 cents every time, and you do it 38 times, you're going to get negative 1.9. Now, why is this negative 1.9 and this is 2? It's because of rounding, right? This isn't exactly 0.92. This isn't exactly 0.97. This isn't exactly 5 cents. You're losing about 5 cents. But it's exactly the same idea. Now, this brings us to the question, why do people gamble if on average they lose 5 cents every time? It's because people, when they're gambling, are risk-loving. Right? They have to be, right? The fact that humans are sometimes risk-loving is the only reason why casinos exist, because they could not exist if the payoff was on average the same, if it was 0, if you on average just didn't lose any money at all. Because if you didn't lose any money at all, then on average, the casino doesn't make any money. Not only is that no profit for the casino, that's also no money to run the casino, no money to pay the staff, no money to take care of the rent or the overhead or the accountants or all the other things. Right? This is how casinos make money. It's not evil, or I'm not judging them. I'm saying that some people are paying to be risk averse. I'm sorry. Some people are paying to be risk loving. Some people pay to be risk loving. And when they play roulette, they're paying about 5 cents every time. This is also why people say that on average, in the long run, casinos win. Right? Because they have to build the odds that way. And you can see too that there is this balance that the casinos have to play. Like, why is it 35 then? Why isn't it 30 or 20? Why don't you only win 20 when it lands on it? Well, because competitive pressures on the casino bring it up, right? It could only be like maybe you only win $2. If that's the case, no one would play. Right? There is a certain amount. Risk loving is a spectrum. Risk loving is a spectrum. And casinos have to compete against other casinos. Casinos also have to compete against people just not playing. Right? You don't have to gamble. Unless, you have maybe some addiction, but you generally don't have to. Right? People can walk away. So this is sort of maybe the highest that they can offer, and still make money, still stay afloat. And that's going to be true of not just roulette, but of slot machines, of poker, of any game you play. That's why, in order to make money at a casino, you have to get a lot of customers. You have to get a lot of people playing these games, because a nickel ain't going to cover rent. You need a giant truckload of nickels. People, though, can also be risk averse, and companies can make money that way too. Companies make money by people essentially willing to pay to avoid some uncertainty. Right? That's being risk averse. Suppose there was an insurance policy that covered this, maybe it was some sort of particular car accident that only had a 1% chance of happening, but if it did happen, it cost people $1,000. That means on average, the expected cost is 10. Of course, an expected cost is just a negative expected value. So you could also say the expected value is negative 10. It's the same idea. Well, if you have an expected cost of 10, that doesn't seem like a big issue. It's $10. But keep in mind that most people pay nothing, right? Because the accident doesn't happen. But a very small percent of people get hit really hard. So people are willing to pay a little bit more than 10 to avoid ever having to worry about that nightmare scenario. If you have any kind of insurance, you might have thought about this, even though, like, especially for auto, right, by law, you have to have insurance, but you might have extra insurance, or you might have supplemental insurance. It's exactly the same idea, right? You might be willing to get that because you are terrified of the nightmare scenario, and understandably so, because the nightmare scenario can be pretty damn bad. Imagine an insurance policy costs $15, so you could avoid that problem. That seems like a pretty good deal, honestly. $15 to never have to worry about a $1,000 nightmare scenario? Sure. A lot of people would take that. Right? Peace of mind. That's what they sell. That's what some of the ads say. Peace of mind. People are being risk averse. They are choosing this one, 15, even though it is, okay, people are being risk averse. They're choosing this, which is a negative payoff, negative 15, over this, which is a also negative payoff, negative 10, but it's larger than this. The only reason why they do that is they're risk averse. So from the insurance company's perspective, let's imagine that, I don't know, there's 1 million customers. Well, that means that they make 15 million in revenue. However, 1% of the time, so 1% of 1 million is 10,000. The customers cost $1,000 each. 10,000 times 1,000 is 10 million. Or, of course, you could have just done this simpler and say 10 million times 10. I'm sorry, 1 million times 10, also faster. So we have 15 in revenue from insurance premiums. We have 10 million in the payouts, which leaves 5 million to cover things like operating costs and worker salaries, insurance adjusters, profit, and so forth. Now, granted, if you're like, well, 5 million is still a lot of money, it's like, that's true, but I just totally made up these numbers, right? It's just an illustrative point. Maybe the insurance premium is only $12, and you're only making 2 million, right? Whatever it is. Maybe it's 15, I don't know. Maybe it's 20, I don't know. But it does illustrate this is how insurance companies make money. Because people tend to be risk averse, and so they're willing to pay a premium to avoid something that has technically a lower expected cost. Now, if you're interested in saving money, this is why some people say, look, if you are in a position where you could possibly absorb the nightmare scenario, be your own insurance company and get the cheapest insurance that is legally allowed, the most cut rate that's allowed. And then just put that money in your bank and save onto it and save it. And you will come out ahead. because then you don't have any workers to pay. The other thing too, another reason to take insurance, and this gets into more of the economics about moral hazard and so forth. If you're someone that gets into a lot of accidents, right, maybe that 1% isn't 1%, but 2% or 3%, then you might actually come out ahead by getting insurance. Obviously, insurance companies know that. They try to figure out what percent kind of person you are, and premiums adjust accordingly. So it's this little game of cat and mouse that's sometimes played. Now, I'm working with very clear probabilities, and we should draw a distinction between probability and uncertainty. So genuine uncertainty, I would say, a probability is we know the probability of like an accident happening, or a 7 coming up on the roulette wheel, or 10% chance that it'll take X amount of time for demolition. In practice, a lot of things are uncertain, where we don't even know the probabilities. That's a very common thing. I mean, a person's attitude toward risk is not the same as their attitude toward uncertainty. If we're talking about probabilistic payoffs, where we can identify how likely is different scenarios are, then yeah, we talk about attitudes toward risk. Risk loving, risk neutral, risk averse. We talk about that in general, it's just part of the lingo. But when we talk about true uncertainty, we don't even know what the likelihood is. I have no idea how likely one thing will happen or another. Well, generally people have a tendency to not like ambiguity at all, under all circumstances, and that is a categorically different thing. Right? If we have no idea what's going on, this is what we call uncertainty, sometimes called genuine uncertainty. As I sometimes say, as language, this is uncertain or this isn't clear, because I don't know what the result will be, even if I know the probabilities. But genuine uncertainty, in that true sense of the word, is you don't even know you don't even know the probabilities. Will this movie succeed or fail? I have no idea, right? That would be genuine uncertainty. We don't do too much with that in this class, because if you don't know the probabilities, you can't do any math. There's not much to do except, I don't know. Right? But I do want you to be aware of that terminology, because it sometimes comes up, right? This is a genuinely uncertain time. We don't even know what the probabilities of X, Y, and Z are. I have no idea. Also keep in mind that risk averse and risk loving is a spectrum. It is not simply categorical. So just because a risk averse person prefers $5 to an expected value of $5 does not mean that they're going to prefer $4 to an expected value of $5. Some of them might, but some of them might be only slightly risk averse, saying, if it was $4.50, I'd be indifferent, but $4, that's too low. Right? To take an extreme, just because if you're saying to yourself, okay, what would you rather have? Would you rather have $5? Or would you rather have, this 1/4 times 20? If you're saying, $5 definitely. Well, would you rather have 3 versus 1/4 over $20 divided by 4? Would you rather have 2? What would you rather do? Would you rather play this dice game, or would you rather have 1 penny? Generally at that level, even the most staunchest risk-averse person is saying, no, let's roll some dice. So it is a spectrum, right? Don't be stupid about it, right? There is a range of risk aversion, and there's a range of risk loving as well. Obviously, if I made this 500, right? No risk loving person will say, I'd rather possibly get 20 than definitely cancel out getting 500. Right? Obviously people would always take 500. The reason why we use this to illustrate the idea is because this expected value is the same thing. And so obviously if anyone tends toward one or the other, then that's clearly they are somewhere on one spectrum or another. Here's another application of expected value. negligence. So if we imagine if something happens, a worker is hurt or a customer is hurt, and the company that employs the worker or provides the product, if the company could have done something to have prevented that harm, should they be held liable? Should they be held negligent? Should the firm be punished if someone is hurt because of company didn't do something? Should that be the case all the time? And I'm not saying that, oh, the customer did something really stupid or the worker did something really stupid. I'm saying it wasn't necessarily the worker's fault, it wasn't necessarily the customer's fault, but should the company always be held responsible? And before you say, oh yes, definitely, think about all the possible things that can go wrong. And think about that there is a range of very bad things to things that are pretty trivial. For example, let's imagine that I'm outside and I'm walking in front of a store, and I go to like a little corner of the store's outside area, place where people usually don't go. And because it's kind of in the shadows, maybe it was cold recently and most of the snow is melted or most of the ice is melted, but because this little corner of the store's outdoor area is in the shadows, there's still a little patch of ice there. And I didn't notice it, and I slip and I fall and I, stub my toe or slightly injure myself. Should I be able to sue the store? Like, I didn't do anything wrong. It's not like that area was blocked off. I could go there. But is the store, should they be held negligent because that unusual thing happened? No, two things are going on here. One, it was a very unlikely thing to have happened. I went to a place normally people don't go. In addition to that, it happened to be frozen, even though all of the ice is melted, because of the weird location where it is. Unusually, there's a little bit of ice here. So this is a very unlikely thing to happen. That confluence of events of someone being there and there happens to be some ice, very unusual. And then what happened when I slightly hurt myself? It wasn't a big deal. That seems like a really small thing. Similarly, we'll go the other direction. If we say, let's imagine that it is in the middle of winter and lots of things are frozen over and this is a high traffic area and I really fall and I like break a hip or something. Well, that's a very different thing. In other words, we're talking in terms of probability and outcome. We're talking in terms of expected value. To sort of organize our thinking a little bit on this. Let's imagine, just to simplify things, 4 different possibilities. Right? So the accident can either be common or rare, and the harm can either be high or low. Now, of course, there's a spectrum of harm, there's a spectrum of rarity, but just to keep things a little simple, let's just recognize that these 4 possibilities. If the accident is common, the harm is high, then the expected harm is really high. This is a big problem. This is the big danger. However, if in the case of me slipping on some little quiet corner of some area and slightly hurting myself, it's very unlikely to happen. It's not a really big deal that it did happen. It's a tiny problem. But now these two are the interesting ones. If something is, if maybe, the accident is rare, but rather than stubbing my toe, I broke my hip, right? That's a big harm. Well, that's a moderate problem. Yes, it's bad if it happens, but it's unlikely to happen. Similarly, let's imagine that I'm unlikely to hurt myself severely in a high case that I slip. Maybe I sprain my ankle, stub my toe, but it's a high likelihood that I will slip. That's also a moderate problem. What expected value teaches us is that these two scenarios, though they seem very different, a rare accident with a big problem or a common accident with a tiny problem, they are mathematically the same. Small value times a big value, or big value times a small value. Well, big times small is the same thing as small times big. Mathematically, they're the same. So for common and dangerous accidents, like here, it makes sense to hold the company negligent. You really screwed up. For rare small problems, it doesn't really make sense to hold the company negligent. Right? That's not really a big deal. For these two, maybe. But let's go even deeper. P is the probability the bad thing will happen. L is the cost of the accident, the cost of the bad thing. This is, of course, an expected value. Obviously, the cost is always negative, but for purposes of our, it's a negative value. But for our purposes, it's expected value, right? It's the probability of a bad, it's the probability times a magnitude if it happens. So, should a company be held liable? Well, in order to figure that out, legal scholars have concluded it depends not just on the expected cost of the accident, the expected value, but also how hard or easy it is to avoid the accident, which we call B for burden. If the burden that a company would pay to avoid the bad thing is less than the expected cost of the bad thing, then the company is held negligent. And we call this the learned hand rule. If you think that's a weird name, it's because the judge's name who came up with this was called learned hand. So let's just go through a quick example so you can see the logic here. Now, I should say in practice that in courts of laws, they don't necessarily assign actual numerical values, though they might, but they could just do as a stylistic mental model. But what I like about it is it's a really cool application of expected value, because that's literally what's going on, right? If we think about my example of like slipping and falling and hurting yourselves, it's like, well, what would cost the company of making sure I don't slip and fall and hurt themselves? And what would be required of that? Well, how would you do that? Maybe you put a lot of salt down or a lot of sand down on the ground to create resistance so that I won't slip and fall. And that's super reasonable, except if it's really, really bad. Maybe it's a very, very thick ice, for example, then that might not be sufficient. So the probability might actually go up based on the circumstances, and the burden also goes up. And then it's not really clear what happened, and not really clear what should we do. Right? Maybe it's really hard to prevent it. Maybe I was walking around at 3 o'clock in the morning, and we had just gotten this frost. We had just gotten this ice. Is it reasonable for the company to hire somebody to put ice down to put salt down as soon as the ice forms? That seems like a very high and unreasonable burden. And notably, the probability of being out in the middle of the night, someone being out in the middle of the night to slip on ice, that's pretty low. So you can see how, in that circumstance, okay, maybe we shouldn't hold them liable. Maybe it's not really their fault, even though no one really did anything wrong. There's a court case involving a woman who got out of the department store. As she was walking out of a department store, she did not see that there was a step to go down when you leave. There was a sign that says watch your step, but because of the way the light reflected off of the buildings at that particular time of day, it temporarily blinded her, and she did not see the step, the sign to go step down. She didn't see the step down itself, and she tripped and she fell, and she hurt herself. I think she really hurt herself. It was pretty bad, but she took to court. She's like, you should have had a way to stop that. She said, like her lawyer said, you should have put an awning out to block the sun, extending out into the sidewalk. And then she never would have been blinded. And then she would have seen the sign. And then she would have stepped down. She wouldn't have hurt herself. Right? So she's arguing that this probability times this liability is relatively large compared to the cost of putting some sort of awning out there. And this is what the lawyers fought about in their arguments. How big is B? How big is P? How big is L? L is actually pretty small. Like you could really hurt yourself, but you probably won't because it's just one step, not like 18. And the circumstances that resulted in her not seeing a sign are shockingly low. Shockingly low, right? The probability of that happening, the way the light hits the buildings and so forth at that time of day, and someone has to be going out that time of day, and the cloud cover and the weather and everything like that. That's very, very low. And then we think about the burden. Not only does it cost money to install such an awning, it costs money to maintain it. There might have to be special permission from the city to extend it out into the sidewalk. It can block views of the interior, which can harm business because the windows are a form of the advertising to show things. So if you block some of that visibility, it's costly for the company in that way too. So then they argue about the burdens, and the judge is like, yeah, this is stupid. If B is greater than PL, you're not held negligent. Sorry for bothering you. And I will see you then next time.